Good morning to everybody. I'm pleased to be here for this conference and thanks for this kind invitation. In this presentation I will discuss some issues concerning landslide monitoring and rapid mapping, and in particular I will talk about satellite radar interferometry and multi-sensor drone, which are two different techniques that we are currently using for landslide monitoring and mapping. Let's start with landslide SAR interferometry. First of all, I would like to say a few words concerning the landslide velocity. You know, this is the landslide velocity classification occurred in advance, that landslides can have different velocities from extremely low to extremely rapid. Extremely low, which are millimeters per day, to extremely low, sorry, which are millimeters per year, to extremely rapid, which are landslides that are moving several meters per second. This landslide velocity related to SAR means that we have different type of using radar data. In particular, we can use satellite images, or we can use the ground-based radar systems. Especially concerning the satellite radar interferometry, this technique is able to monitor, in particular, landslides that are classified in landslide classification system as from slow to extremely slow. Why, if we deal with landslides that are moving faster than 1 meter per year, satellite radar interferometry is not the more appropriate technique. Here we have to decide for other type of technique, such as ground-based radar interferometry or other type of instrumentation. These are some pictures of the satellite SAR satellites, and these are all the available data coming from all the available in the past and now at the present satellites, SAR satellites. And you have the here all the years, the different type of satellites which are classified on the basis of the band, wavelength and resolution. And on the basis, on the last part, is the revisiting time. That is the time needed for the satellite to see the same scene on the ground. And in the past, there are some satellites which have been used very much for landslide mapping and monitoring, especially the ENVISAT and the Earth satellite. And actually, there are several satellites, for example, RadarSat and Cosmos SkyMed, and in particular Sentinel, which is the new satellite launched 2 years ago from the European Space Agencies, which can be very useful both in terms of revisiting time and spatial resolution for mapping, but especially for monitoring on landslides. The SAR satellite images can be used, can be analyzed, processed with a technique that is called multi-interferometric InSAR, which analyze and process different images, SAR images, in order to detect in the ground several radar targets on which we can measure the deformation in terms of velocity, and we can also retrieve the time series. The satellite is a circumpolar orbit. This means that it's moving from the north to the south, and this is the descending orbit. Or moving from the south to the north in the ascending orbit. the line of sight of the satellite is lateral to the orbit of the satellite. This is LOS, is the line of sight. In Italy, we have the first national application of this technique, which is the persistent scatter interferometry, in 2009, when the information concerning the movement of the ground for the whole Italy has been was available, freely available from the Environment Ministry and Minister. And this is a map of the deformation where the different colors means the different velocity of the ground. For example, usually when we use this technique, green means that the movement, there is no movement, the ground is stable. When you have a blue color, like in Sicily, here in South Italy, or some part of the north, you have a movement towards the satellite, so means there is an uplift, while when you have red zone, you have subsidence, so a movement away from the sensors. This technique has been used for several applications since the more or less 10-15 years, and especially for the landslide inventory mapping and updating. So it's possible to map new landslides and to update both the perimeter and the state of activity of already existing landslides. This is an example of the Tuscany region in Italy, where we have updated all the regional landslide inventory with this technique. And, but also what is possible to use this technique for, this was an application at regional scale, but it's possible to use the persistent scatter interferometry also at local scale for single landslides. These are 4 pictures of the same landslides. A landslide is a movement located in northern Italy. Is Santo Stefano d'Avito landslides, where in these points are the ground control points, and blue are movements, are two different satellites, Earth and Visant, and 2 different orbits. And both blue and red means that there is a movement, so it's possible for different points to measure the medium velocity and to have a look to the time series deformation. Like this one. This is the time series deformation along the monitoring period. And for a single landslide, it's also possible to compare this data with ground-based, classical, conventional ground-based monitoring data, like inclinometers and stensometers and so on. Another approach for to exploit this technique has been developed by our research group. Is called the PSI Hotspot and clustering analysis, and has been developed in order to better interpret all the data coming from the PSI analysis, because in many times we have a lot of points, deformation points in the ground, and with this tape of statistical analysis we can automatically detect bigger area which have ground deformation. So it's an automatic detection of cluster of points which show a similar movement. So, for example, bigger areas where we have subsidence or uplift or simple landslides. And this is the outcome of this type of statistical analysis, and this is a part of the Tuscany region, and you can see different balls, colored balls. In blue are the area where, because this technique has been developed merging the two orbits of the satellites, so ascending and descending. In these ways, it's possible to define the real displacement vector of my deformation. So in blue, you have the areas with uplift, so areas where you have a predominant movement which is uplift. In red, you have, for example, here in the north, there is Mugello. Mugello is an area, is a fluvial plain in the north of Tuscany, where there is an area, an extensive area of subsidence, which is in red. And why in magenta color, this for example, this one, you have a combination of red and blue. This means that you have both uplift and both subsidence, which are probably due to landslides phenomena moving along a slope. This is some application of, let's say, historical SAR images. Currently, we are developing, we are carried out a pilot project in Tuscany, which is exploiting the use of new SAR images, which are Sentinel-1, which have a very high revisiting time, around 6 days of revisiting time on the same place, and medium resolution, which can be used for more monitoring activities, because until now we have seen activities concerning mapping, detection, and back monitoring. But with this new pilot project, we are trying to use the SAR data coming from the satellites for a more real-time monitoring. This is Tuscany, and it is all the data from the Sentinel data. I remember you that the revisiting time is 6 days. And it is the first application of this technique for, let's say, continuous streaming at regional scale, continuous streaming of ground deformation. And this is a figure with a picture with Sentinel data related to October 2016, ascending orbit and descending orbit. And in this project, we analyze, we process every 6 days the data coming from the SAR satellite, and we compare the new data with the old one in order to detect some trend change detection of the movement and to identify possible acceleration or deceleration of the movement every 6 days. These points are points where during has been identified some trend change detection, and this is an example. Obviously, every 6 days we are performing this analysis, and this is a zoom of the area where we can see this point and the time series deformation, where we can see that at the end there is a slow acceleration of the movement. We would like to use this system for a sort of early warning at regional scale, and so we have prepared a warning bulletin for each municipality of the Tuscany region, and where the colors of these are the municipality of the Tuscany region, and the colors means a sort of alert level where green is no movement, no movement, no trend change detection with respect to the previous images. Then we move to yellow, where we have only one point which has a trend change, until red, where we have within the municipality several points with trend changes. So both per system in time and with an high intensity in terms of movements. This warning bulletin then can be has been seen by the region authorities, so they can decide where to do further checks, especially field checks. So we go to the field and we verify if what type of movements, which is the cause, what type of mitigation measure we can carry out. These are some pictures of the field checks. This is concerning the satellite SAR interferometry. Another type of equipment and instrument that we are currently using frequently for landslide mapping and monitoring is the drone. A drone that is called SATURN, that we have completely developed and within our research group, which has some particular features with respect to the already available drones, which has a mission flexibility, is very light. There is no constraint for cargo area. There is an optimal placement for the sensor, because our final aim is to have a drone equipped with multi-sensor, so with different type of sensor simultaneously, and has an improved and flexible flight time and a power computation acquisition unit. Currently we are using this drone with high resolution camera and thermal camera, because we have these two sensors. We are working with the Department of Physics of our university on the development of an hyperspectral sensor, and with the Joint Research Center of the European Commission, we are working also with the development of a small radar to be put on the drone for monitoring. We have also developed a smaller drone, which is called SATURN Mini, which obviously is lighter than the previous one. It has been completely self-produced by our group with a 3D printer, and has high resistance to wind, and has been designed especially for aerial mapping, because it's not possible to equip with this drone with different type of sensor, but just one sensor, and we use this just for mapping, simple photogrammetric analysis. I show some results, preliminary results of our study with the multi-sensor drone in two different case studies. One is a landslide located in Tuscany, in central Italy, and one is a volcano, Stromboli volcano in southern Italy. In the first case, for Ricasoli, we have done a landslide mapping and characterization, especially concerning extension of the movement and volumes, while for Stromboli we have done a 3D mapping of the Sciara del Fuoco. Sciara del Fuoco is the most active part of the Stromboli volcano, and is completely inaccessible by people, so to have a complete view of this area, the survey with the drone was really necessary. Let's start with Ricasoli. It's a landslide, rotational landslides located in central Italy. Is not only rotational landslides, but also other type of movement like shallow landslides of fall, which are affecting a village, a small village. This site has been equipped with several types of monitoring instruments, inclinometers, wireless sensor network, terrestrial laser scanner, and some consolidation works have been done on the north flank of the village in 2014. We have done recently, from July 2015, 3 drone surveys, one in July 2015, one in March 2016, and one in April 2016, on the north flank of the village where the consolidation works have been done. We have equipped the drone with a high-resolution camera. In this table, you can see some details concerning the flight of the drone and the resolution of the acquisition for the 3 drone survey. And this is the procedure. The flight path, which has been defined before, obviously, the flight, then the GPS surveys at some points, and the creation of the point cloud, and then the DTM. This is the point cloud of the first survey in 2015, where we detected a small landslide in the north flank after the consolidation works. Then the landslides occurred in February 2016, just after we performed the drone survey. And this is the result, the point cloud of the drone survey. And after that, a third drone survey in April 2016. Oops. We have elaborated the process, the images, and creating the DTM, and we have performed some analysis concerning the dimension of the movement and the extension, and also the material involved, making a difference between the different DTMs. And this is a different picture. In red are the areas where there is a loss of material, where at the base of the slope, in blue, you have the areas with the accumulation of material. This is the same picture, and we have performed different profiles, and we have calculated the volumes for the 2 landslides of chord. The landslide 1, which is the bigger, and landslide 2. This is the application to the Stromboli volcano, the Sciara del Fuoco, and we have performed 2 surveys in this case, one in October 2016 and one in May 2017, recently. In this case, we have used the SATURN Mini, the drone, the smaller drone, which has been equipped with a RGB camera sensor, and with a flight altitude of 70 meters, and this is the resolution and the extension of the area, which is about 1 square kilometers. This is the results, and I would like to highlight that in this case we have used the smaller, the SATURN Mini, since the possibility to lose the drone is very high, since is an area a particular area is volcano with very windy and a lot of ashes. So the risk to lose the instrumentation was very, very, very high. Fortunately, we haven't lost the instrumentation. I have a video of this survey. I don't know if there is also the volume, but just to show you the extreme condition, both of weather and mainly related to the volcano activities. These are all the ashes of the volcano. This is the Sciara del Fuoco. Here we are preparing for the survey. This is the smallest drone equipped with the camera. first survey of the Sciara del Fuoco with a drone. So with the point cloud derived from okay, I think it is enough. And in this picture, there is also the movement of the soils from the accumulation, and in red the loss of material, as we have seen in the previous case studies. Okay, I've finished. I don't know why it was the last images, sorry. And I would like to thank all my colleagues, because this work have been done together with my group, research group. And so the last slide was a picture of the research group. So just to show you our group, my colleagues. So thank you very much.